This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. So the plan today is to finish off part 4 of the notes. Okay, so that will leave us with an opportunity to look at problem set 5 on Thursday, and then Friday will be our last lecture, and we'll tie off any loose ends and maybe have a look at an exam from the past. Okay, so there are already lots of exams available on LMS up to 2015. That gives you an idea of what the structure is. It doesn't change, right? But there's a limit to how many exams I want to put up there because your exam is open book, right? So in principle, given that all the questions are roughly the same, right, you'll just be able to just write down answers and take them in with you and, right, not have to work anything out in the exam, right? But there are 4 examples of past exams, and then there are all the mid-semester test questions with work solutions. I won't give work solutions to the past exams, okay? Don't forget to sign up your group for the submission of the report for Workshop 4. Okay, so the link is now available on LMS. All right, and in case you haven't checked, the exam for this subject, if I remember correctly, is the 18th of June. Okay, so that's 3 weeks from today. All right, so plenty of time. So what we're going to look at today is a method for synthesizing feedback controllers that result in the closed loop poles being in specified locations. All right? And I'm showing you this technique because you may have heard of it, and it's often presented in textbooks, but it puts all of the attention on the closed loop poles. Okay? Which, as we know, is not the whole story. Okay, so while this may seem like a very appealing method to design a controller, okay, it has limitations. And those limitations are associated with all attention being put on the closed-loop poles. Okay, and the closed-loop poles will determine aspects of the transient response. It will determine how fast it is and whether or not it's oscillatory, right? But the zeros of the closed-loop transfer functions also have an influence on the transient response, okay? And by just focusing on where the closed-loop poles are, we can easily lose sight also of steady-state performance specifications, all right? So you've got to be very careful when using this method, but it's worth knowing about anyway, all right? It's just another tool in your toolkit. All right, and as I've said many times before, control system design is not about recognising that for this problem I apply recipe A, right? It's about making use of all of your toolkit to address whatever challenge lies in front of you. All right. So the basic idea in pole placement is to specify where you want the closed loop poles to be, right? And we know that the closed loop poles correspond to the zeros of the so-called characteristic polynomial. All right, so if we represent our plant transfer function as a ratio of 2 polynomials b and a, so that'll be given, and we're looking to choose the controller transfer function, which is just a ratio of 2 polynomials p and l, such that the characteristic polynomial, which is given by this, has zeros in specified locations. So if you like, we're going to specify what this polynomial is. Right? You can specify what a polynomial is by specifying where its zeros are. Okay? And so the job is to then find P and L, given A and B, to make this have desired characteristics. All right? So the question is, do there always exist L and P satisfying this equation when we've specified what ACL is? Okay, well, let's think about what this is. Well, it's just a polynomial. And so if our plant transfer function has n poles, all right, then A will be a polynomial of degree n. And if our plant transfer function is proper, then the numerator polynomial B will have degree no greater than n. All right? And so let's say, well, we're prepared to allow the controller to have m poles. Okay, so L will be a degree m polynomial. And if we want our controller to be proper, then P will have degree no greater than m. Okay, of course, it could have degree less than m by just setting that coefficient to be 0. All right. So if we're given a closed-loop polynomial, all right, of degree q, which will have to be less than or equal to n plus m, right? So if you see here, we're taking the product of a degree n polynomial and a degree m polynomial, so the result could be degree n plus m. All right, so the thing that we're trying to shoot for has to have degree less than that. Of course, you could think of it as having degree n plus m and then setting the coefficients of the highest powers of s to 0 as desired. Okay. All right. So the question is, well, when can we find the coefficients of these polynomials, L and P, such that this product is some specified polynomial? Well, we can find out what these coefficients have to be by making this product, okay, which will give us, you know, a new polynomial, and then matching coefficients with the desired polynomial. All right, so if you match coefficients here, right, then you will get, well, taking the product here, we'll end up with the degree m plus n polynomial. So to describe a degree m plus n polynomial, we need m plus n plus 1 coefficients, right? And we're going to get one equation by matching each coefficient to a corresponding term on the right-hand side here. All right? And the number of unknowns we have, okay, is the number of coefficients we have to find in L and P. All right, so L has m plus 1 coefficients, P has m plus 1 coefficients. So in total, we are looking to solve for 2 times m plus 1 unknowns. All right, and we're going to solve for those by writing down m plus n plus 1 equations by matching each coefficient of ACL to a corresponding term on the right-hand side here. All right. So, you know, we know that, if the number of unknowns is equal to the number of equations, then we can potentially get a unique solution. Okay, so that's suggesting that you need to choose the degree of L to be less than or equal to n minus 1, where n is the degree of A. And often we just take m to be equal to n minus 1, right? So that we can arbitrarily set the coefficients here, right? So in the case that you take m equal to n minus 1, then you can arbitrarily choose these coefficients, all right? So if we just write down the equations that you get by matching coefficients on the left and the right here, you can end up with this so-called matrix, Sylvester matrix equation. Okay, so it's just writing down this system of linear equations in matrix form. So let's just do a little example to see how that works. All right, where we're going to take A to be a degree 2 polynomial. All right, G is our proper transfer function, so B will be a degree 2 polynomial or less. Right, and we're going to take M, the degree of L, to be 1 less than the degree of A, right, as suggested on the previous slide. So L will be a polynomial that looks like this. We want our controller transfer function to be proper, so P will also be a degree 1 polynomial or have degree less than that, okay, by, for example, choosing P1 to be 0. All right, so the characteristic polynomial, that's what we want to specify, is just the product of A and L plus the product of B and P. So if we just write down what that is, okay, so if I take, the product of this polynomial and this polynomial, that's this here, and add to that the product of this polynomial and this polynomial here, and expand everything out, you'll end up with a degree 3 polynomial, because here I'm taking a product of a degree 2 polynomial and a degree 1 polynomial that will result in a degree 3 polynomial, same here. Okay, and so if we now group terms together according to the corresponding powers of S, okay, our Laplace variable, then we'll find that the coefficient of S cubed will be this, right? It comes from this multiplying this, which gives you S cubed, and it's A2L1, right? We can also get a cube from this term here by multiplying that with that, so that's where the B2P1 comes from, all right? We can get S to the power of 2 by taking the product of that and that, that and that, that and that, that and that. That's what gives all these coefficients here, and so on. Okay, and so what we want to do is choose L1, L0, P1, P0, such that this product, okay, which can be re-expressed like this, is a specified, that should be cubed, polynomial. Okay, and we're specifying what this polynomial is by saying what the coefficients here are. All right? Yeah, specifying these coefficients specifies where the zeros are, right? Because once you've got all the coefficients for the polynomial, you'll fix the zeros. Or if you're given the zeros, you just expand out, you know, the factored form of the polynomial to find out what these coefficients are. Right? So we're going to say that we want this to be the result, and we say that we want this to be the result by specifying these coefficients. And our job is to choose these coefficients, right? So that this matches this coefficient, this matches this coefficient, this matches this coefficient, and this matches this coefficient. So if you just write that out as a matrix, all right? So equation where each row corresponds to matching one coefficient in the desired characteristic polynomial, right? So we're going to just write down a little vector of those coefficients, C2, C1, C0. Okay, so that's the result that we want, all right? And we're going to get a matrix, and that matrix is going to multiply L1, L0, P1, P0. So this is a vector now constructed out of our unknowns, right? The coefficients of the controller transfer function polynomials that we're trying to find, all right? And matching coefficients here, well, C3 must be A2 times L1 plus B2 times P1, right? So if we write down what this matrix, the first row of this matrix has to look like, A2, right? 0, B2, 0, right? So that we get A2 times L1 plus B2 times P1, and we need to make that equal to C3. All right? We get the second row of this matrix by equating this coefficient to this, C2. All right? And what do you see? Well, you see that C2 will be A1 times L1, right? It'll be A2 times L0 to give me that term there. Then you need B1 times P1 and B2 times P0. All right? So making the second row of this matrix in this way corresponds to equating C2 to A1 times L1 plus A2 times L0 plus B1 times P1 plus B2 times P0, right? And so you can keep on going like this, right? So now we move along to the next coefficient, right? And what you see is that we have to write, we have to get A0 times L1, right? So we'll get that by putting A0 here. And we need to get A1 times L0 to give us this term here. We need to get B0 times P1 and B1 times P0. All right, we're left with one coefficient to match, C0, and C0 must be given by this, all right? And we get that by doing this, All right, so this is just, writing down a system of linear equations obtained by matching coefficients of some polynomials in matrix form. All right, so what you can see is that there's a bit of a pattern here. As long as you order the unknowns in this way and the knowns in this way, you can see that the first column here just consists of the coefficients of the polynomial a, the denominator of the plant transfer function, listed in order until we run out, and then we run out, we put zeros in, right? And then move to the next column, we put a 0 at the top, and again, list the coefficients down. All right? And that's the pattern that's being drawn here for higher order polynomials. So you see, you write down all the coefficients of the A polynomial, all right? Then you put a 0 and write them down again, put a 0, write them down again, so you get things across these diagonal lines matching up in the way shown here. Okay? All right, so, why is this useful? Well, given these things here, we're trying to find these things here. And of course, if we know what this matrix is, which we do because we're given the plant transfer function, we're given the polynomial A and we're given the polynomial B, to figure out what these are, we just need to invert this matrix, right? And multiply the inverse of this matrix by this vector here, and that will give us the solution. Okay? So the question is, when is this so-called Sylvester matrix, all right, which in general has this form here, when is it invertible? Well, it turns out that it's always invertible, right? So you can always solve this system of equations, provided your polynomials B and A are co-prime. They have no common factors, which is something that we've assumed is a standing assumption the whole way along, right? So in other words, you can always place the poles of the closed loop in arbitrary locations, right, by solving this system of equations. All right, provided your plant transfer function is expressed as a ratio of two polynomials that are co-prime. But what's the point of not having these as co-prime, right? Because you can always simplify. If they have a common factor, you just cancel it out. Why carry it around? Okay, so you can always solve this equation, right? So that's what this stuff here is about. It's about proving that, that this Sylvester matrix will be invertible if and only if the polynomials A and B are co-prime, which is a standing assumption. So the way the proof goes is by saying, well, let's suppose that A and B are not co-prime, all right? So in other words, they have a common factor, S plus Z. That's what it means to be not co-prime, all right? If that's the case, then you can write down this equation, right? Which looks very similar to the equation here that gives rise to this system of equation by matching coefficients, right? So where does that equation come from? Well, it comes from the fact that if this is true and this is true, then AS on BS will equal A tilde S on B tilde S, right? Because when you do A on B, those factors just cancel out, leaving you with A tilde on B tilde. And if you rewrite that equation, you get AS B tilde S is equal to A tilde S times B S. But that's just that, right? Once I take this term over to the other side. Okay? So this looks like our characteristic polynomial equation, where we have B tilde instead of S, instead of L, and we have A tilde instead of P, right? And we're saying that this expression is equal to 0. So it's like saying, well, that's equal to the polynomial with all coefficients being 0. Right? All of these guys being 0. Okay. All right. So if this is the case, then this is 0, and that's 0 if and only if the Sylvester matrix times this vector of the unknowns, the L and the P coefficients, which ended up here in a particular order, right, is equal to 0. Okay, so that's telling you, well, either all of these guys are 0, right, because any matrix times a vector of zeros gives you 0, all right, which doesn't really make sense because, you know, our plant transfer function, well, I've written this the wrong way around, right, but B on A, it doesn't matter which way you write this around to get this equation, right, but our plant transfer function, G of S, is equal to B of S on A of S, so it doesn't make sense that A is 0, right? B could be 0, but if B is 0, then your plant is just 0, okay? So that's probably not going to be the case, right? And the other way that this could hold is if S is not invertible, right? In other words, S has non-zero vectors in its kernel, right? The kernel of multiplication by a matrix is just a set of all vectors that get mapped to 0, right? And there will be such non-zero vectors if S is not invertible. If S is invertible, then there are no non-zero vectors that get mapped to 0. All right? So we've shown that, not co-prime implies not invertible, right? So I'm just denoting co-prime by X and Y just to show you the propositional logic that leads to this conclusion. Well, if that's the case, then X must be implied by Y, right? So if S is invertible, then A and B must be co-prime, right? So we've shown one direction of this if and only if, okay? And you get the other direction of this if and only if by following a very similar argument as presented here, right? So again, we start with the opposite direction. Suppose that S is not invertible, then this guy here must have a non-zero solution, all right? So you write down what those guys are, but then you end up with this situation here, which we exploited here to arrive at this equation in the first place, right? So if A and B are co-prime, then S must be invertible by following, similar conclusions derived from propositional calculus, right? So the bottom line is, if A and B are co-prime, then S will be invertible. And if S is invertible, we can always solve for these unknowns given these, right? Because these unknowns will be S inverse times this vector, okay? All right, so this is telling us, well, you can always place the poles wherever you like. That's the conclusion, all right? All right, so that's just summarising stuff that I've just said in words, right? So we get our unknown coefficients of the controller polynomials by multiplying the coefficients of the desired characteristic polynomial by the inverse of the Sylvester matrix, all right? And you don't have to worry about the potential for pole zero cancellation between the polynomials of your controller and the plant, which we know can be a problem if the cancelled poles are and zeros are in the right half plane. That's a big no-no, all right? But that can't happen, right? Because if it did, those factors would end up being factors of the specified closed loop polynomial, right, which we've seen before. That's what happens with cancelled poles and zeros between the plant and the controller. And you're specifying what this is, right? So if this only has zeros in the left half plane, you can't end up with a situation like this, right? So there's nothing to worry about, okay? You can never end up with pole zero cancellation by following this procedure, or at least not pole zero cancellation in the right half plane, right? Because you're specifying that this has no factors in the right half plane, and if there were pole zero cancellation in the right half plane, it would appear as a factor of the characteristic polynomial, which we've seen before, right? So it can't happen. You don't need to worry about it. It can happen in the left half plane, though, right? All right, so let's just look at an example. All right. So let's suppose that we're given this as our plant transfer function. All right. Seems like a pretty benign system. It'll be stable. It'll have two poles in the left half plane. Okay. It'll have, reasonable damping. Right. The natural frequency here is 9. Square root of 9. Right. 3. Twice the damping times the natural frequency is equal to 5, right, this term here. All right, so the damping here will be, 5 on 2 times 3, right? So, yeah, that's not that small, so it's pretty well damped already, all right? So this is our A polynomial, right? This is your B polynomial. Really, we're saying that B is b2s squared plus b1s plus b naught, with b2 equal to 0, b1 equal to 0, and b naught equal to 1. All right, which you need to, take note of in order to be able to, figure out what these coefficients are going to be when you're building the Sylvester matrix. All right. Okay. So, let's choose the controller so that the degree of its denominator is 1 less than this, right? Because that will give us the right number of equations, right, to be able to solve for the number of unknowns that we have. Okay. It'll make the Sylvester matrix square so that you can invert it. And let's suppose that we want to place all of the closed loop poles in the same location. Right, seems like a reasonable thing to do. Why not? Right, put them all on the real axis at minus c, where c is some positive number. So they will be all in the left half plane. So we're going to get a stable closed loop. And by specifying the closed loop poles to lie at minus c, we're going to get transients in the response decaying like e to the minus ct. Okay, so we can control how fast they're going to decay, right, the components of the transient response by choosing C, right? The bigger we choose C, the faster they will decay. What we're not having any authority over by following this procedure is how those components of the transient response add up together, right? Because that's determined by the zeros of the closed loop transfer functions as well as the poles, right? When you're doing the partial fraction expansion, right, the whole transfer function affects how each component contributes to the overall response, and all we're specifying here is what the denominator of that transfer function looks like. Right, so this is why you have to be careful when applying this method, because we're just focusing all our attention on where the poles are, right? But that's not the whole story, as we know. Okay. All right. So if you just write down what the Sylvester matrix is, remember that that corresponds to just writing down the coefficients of the A polynomial in order. So that A2 is 1, A1 is 5. A0 is 9, right? So they go down there and you put a 0 in, then you put a 0 in, and then you write down the coefficients again. All right? This is your B2 equal to 0. This is your B1 equal to 0. This is your B0 equal to 1. Then you put a 0 in. There's your B2 equal to 0, B1 equal to 0, B0 equal to 1. Okay? So, we want the Sylvester matrix times the unknowns to equal the coefficients of this specified polynomial, which we've listed down here. So the unknowns will be the inverse of the Sylvester matrix times that vector. Okay? This is what the inverse of this matrix looks like. All right? So we can say, well, L1 is just going to be 1, right? L0 will be, 5 minus 5 times 1 plus 1 times 3c, right? So it'll be dependent on how we choose c, right? And so on for the rest of the coefficients in the numerator of the controller. All right? Now, what can we note here? Well, you can see that L0 will be a negative number, right, for C less than 5/3. So what? Well, if this is a negative number with L1 equal to 1, then we're getting a controller with a pole in the right half plane. We've never seen something like that before. All right? We know some closed-loop transfer functions inherit zeros at the locations of poles. And so we're going to get a right half plane 0 in our closed-loop transfer functions because of the pole of the controller being in the right half plane. Right? So I'm trying to just highlight, the pitfalls of looking at these things. You can get some unexpected stuff happening, right? And it's because all of the attention is being focused on where the closed-loop poles are. We're not paying any attention to any other aspect of the closed-loop transfer functions. All right? So there's already something weird happening. If you choose C equal to 2, it turns out that the DC gain of the complementary sensitivity function, the ratio of the open loop transfer function and 1 plus the open loop transfer function, will be negative. All right? So, if we've got our closed loop, the complementary sensitivity function is the mapping from R to Y, okay? And we're saying that the DC gain for this choice of C is negative. So if I put R, in the time domain, R of T, if I made R a step, right, then you're going to get Y probably doing this, right? It's going to go in the wrong direction because it has negative DC gain. All right, again, why is this happening? Because we're not paying any attention to these sorts of characteristics of the closed loop. We're putting all of our attention on where the closed loop poles are, right? And that's, it doesn't tell you the whole story. Why would you want it to go in the wrong direction, right? You're trying to get Y to follow R. Okay, so the transients, we've controlled how long it takes to reach steady state by choosing C, but we've ended up, for quite a reasonable choice with a transfer function from R to Y with a negative DC gain. I mean, if I push it in one direction, it moves in the opposite direction. Probably not what you want. Right, so you've got to be careful. Continuing on this example, this shows what happens when you choose C equals 1. When you choose C equals 1, we're ending up with a closed loop that has a complementary sensitivity with positive DC gain, right? But it's large, right? So I'm putting a unit step in, and what I'm getting out is a steady state value of 19. Well, that's not very good tracking. Sure, the transient dies away, after 5 seconds because we've chosen a time constant of about 1. But, you've ended up with a DC gain that you probably don't want. All right? Even though you've chosen, quite a sensible number here for the closed loop poles. With C equal to 3.8, all right, then, we end up with the problem we saw before where it goes in the wrong direction. Right? It's going, the steady state value is negative when we've put a positive step in for the reference. So it's not giving you very good reference tracking, right? This is choosing C to be 4, right? And, this is like you end up with your controller here has the form of a lag or a lead compensator, right? And it turns out that, for this particular choice, you end up with the pole of the controller being closer to the imaginary axis than the 0, so that's like a lag compensator, but it has very low gain. And so you see that the steady state response, instead of being at 1, is like, 0.015. Again, not very good tracking performance, right? Choosing C to be 10 seems to do a bit better, but the output response to a step in is still only 0.8 instead of going all the way up to 1. All right. So you've got to be careful, right? It's not obvious how to choose the location of the closed loop poles, right? That's the point of this example, right? It's just to show you that this is no silver bullet that you can just magically apply blindly and expect a good outcome, right? So there are some limitations. And really what we're seeing here is that, by just putting all of our attention on the location of the closed loop poles, we're not taking into account steady state performance specifications. Right? That's really the problem with all of these, is that in steady state they're not giving us what we want. They're giving us the right sort of transients that die away quickly, but in steady state we're not getting what we want. All right? It turns out though that you can combine pole placement with the internal model principle, right, to get desired steady state behaviour. Remember, the internal model principle was all about getting desired steady state behaviour, right, by ensuring that the open loop transfer function has appropriate open loop poles, right? Open loop poles that coincide with the zeros of the generating polynomial for the reference or disturbance that enters the closed loop. Okay. So that's what this is about, is saying, well, we know that if we want 0 steady state error for a step here, then we're going to have an open loop pole at s equals 0, right? So let's force it in there. Okay. If this is a sinusoid of frequency 1, we know that in order to get 0 steady state error, the open loop transfer function will have to have poles at s equals plus j and minus j, right? So let's force it in there if we know that that's what we want to achieve in steady state, 0 error for a sinusoidal input. Okay, and then you can place the closed loop poles, right, by absorbing this fixed thing that you've inserted into the open loop to ensure satisfaction of steady state specifications. You absorb that into your plant transfer function to get your augmented plant transfer function that makes sure that the open loop will have poles in desirable locations from the perspective of steady state error performance, given knowledge of this signal. And then you place the closed loop poles in the way we've just seen by choosing the controller. And in the end, the controller will be the product of this and this. Right? So for the purposes of synthesizing this, you absorb it into the plant, but the controller you implement in the end will be the result of synthesis combined with this. All right? So just very simple idea that now gives you a handle on steady state specifications, which via this example we saw was not possible by just focusing on where the closed loop poles had to be. All right? So, here's a little example. We have a plant, it's unstable, has a pole at s equals 1. Let's suppose that we want exact tracking of a true radian per second sinusoidal reference. So the internal model principle tells us that we need the open loop transfer function to have, which is the product of the controller and the plant transfer function, to have poles at s equals plus or minus j2, right? So the corresponding generating polynomial is s squared plus 4. All right. So we now absorb that into the plant, right? So we've got an augmented plant transfer function, which will be 1 on s plus 1 times 1 on s squared plus 4. Okay. So your A is now the product of these guys, right? Your B is just 1, right? So that's what's written down here. And we're looking for now controller transfer functions, but it's not the whole controller, it's just, you know, this bit here. Ultimately, these bits get combined to give you the controller. And we choose the degree of that controller to be 1 less than the degree of the augmented plant denominator, right? That allows us to get a square matrix here, basically. And you need a square matrix for it to be invertible. All right. And here we're saying, well, we want the desired closed loop poles to be consistent with the zeros of this and this, right? So this is fast, right? And this is reasonably well damped, right? And that's consistent with having not a degree 5 polynomial, but a degree 3 polynomial. And we can get away with specifying these to be 0 in this particular case because B has degree 2 less than the degree of the augmented A, right? So when you invert this matrix, it's still lower triangular, right? And by specifying these coefficients to be 0, you ensure that these two coefficients will be 0, right? Because the inverse of this matrix will still be lower triangular, and you're saying that these coefficients are 0, so that will give you L2 equal to 0 and L1 equal to 0, right? And the point of doing that is to ensure that once you absorb this into the controller that you've synthesized, you end up with something that is proper but not strictly proper, all right? Whereas if we'd set these coefficients to be non-zero, right, by perhaps putting another 2 fast poles in here, okay, then the controller you implement would have to be more complicated, right, because it would have a degree 4 polynomial on the bottom instead of a degree 2 polynomial. So you can't always do this. It just works out this way because B has degree 2 less than this guy, which makes all of these terms in here 0. All right, which gives us this lower triangular structure. And when you invert a lower triangular matrix, you end up with a lower triangular matrix. Right, but this is just illustrating, you know, how you can exploit degrees of freedom in here to reduce the complexity of the controller, given that we've already specified this as part of the controller to meet steady state specifications. Right, and you don't have to do this. I could put 2 more faster poles in here that would make those non-zero, right? Just that my controller now would be more complicated. It would have 4 poles instead of 2. That's all. All right, but you can't always do this. It's really relying on the fact that B is special here. Okay. Anyway, so you know, there are some things that you can do to overcome the sorts of limitations revealed by this example, and you know, to get steady state performance specifications, use the internal model principle. All right. So this is just a little, you know, continuing on this example to show you what happens with this controller. Okay. You know, you can't, you know, it's giving you this sensitivity function with a deep notch at 2 radians per second, all right, which is how you get 0 steady state error for a sinusoidal input with a frequency of 2 radians per second. All right. Okay. So, just continuing that example. Now, you can use this technique to choose the parameters of a PID compensator, right? When your plant is approximately second order, right? So it's just, you know, going through the same steps, right? Instead of parameterizing your PID controller like this, which is one of the ways we saw, but it's no unique way of doing it, you can just write it down in terms of, you know, the objects that we've been dealing with today, go through the same procedure, right, to ensure that the parameters of your PID compensator result in closed loop poles in specified locations. All right. Now again, you know, you've got this, you know, works if your plant transfer function is close to being second order, all right, at least over the desired bandwidth of your closed loop from the perspective of the, you know, the frequency at which the complementary sensitivity function rolls off. Okay, but as we've seen by these examples, right, this is no magic, right, and you've got to be really careful about how you choose the desired closed-loop pole locations. All right. So really, all this is just algebra. That's all that's happening here. It's just linear algebra being used to solve a problem, right? But the problem that we're solving isn't the whole picture. I think that's what I want you to take away from this. So you've got to be very careful how you use this. So, choosing the right closed-loop poles is, the proverbial million-dollar question. It's not easy to do, right? And there'll be always a little bit of trial and error where you choose the poles, then actually see what you get out in the end, all right? But at least it makes the selection of controller parameters a bit more systematic, right, than what we've seen before in terms of achieving desired loop shape. Okay. There's some ways of making sure you get the right steady state behaviour, as we've seen, by exploiting the internal model principle, right? And there are some simple rules of thumb that you can follow, right? So if the plant has a fast pole beyond the desired closed loop bandwidth, right, which will relate to where you're trying to put the closed loop poles, at least the dominant ones, then this should be matched by a closed loop pole, right? So you've got to use information about the plant to set the location of one of the closed loop poles. And the rationale for this is that that the output sensitivity function will be 1, okay, at high frequencies, right? If we're going to be getting sensible performance, and the sensitivity function will have a 0 at any uncancelled open loop pole, right? So if you've got a fast open loop pole, right, then the sensitivity function will have a 0, right? Zeros make Bode plots kick up, right? So if your plant has a fast pole, then the sensitivity function will have a 0 at a high frequency, making the Bode plot kick up. But we know that the sensitivity function should be flat, right? And so, if it's ending up flat, it's telling you it must be going down. So when the 0 that the sensitivity function inherits from the plant having a fast pole kicks it up, makes it 1. And if that's happening, it's suggesting that the sensitivity function must be peaking up before it gets to 1, right? So to avoid that, you can make sure that there's a closed loop pole at the location of the 0 that's pulling this up to make it flat, so that you don't get this peaking, right? And a similar thing when the plant has a slow 0, then you know that the complementary sensitivity function will have a slow 0. And we've seen that when you have situations with like this, where the poles are faster than this, you can get lots of overshoot in your step responses. Okay? But if you put a closed loop pole in that tries to cancel that guy, then you won't get that effect. All right? But again, these are just little rules of thumb to try to make this thing work, right? But I think you just need to be careful when trying to use it, right? And like with the loop shaping examples we saw, you do the design and then you do some simulations to see what you actually get, right? Because a lot of this stuff will be based on approximations or not paying attention to the full picture. All right. So, in my opinion, the best way to think about the design of single input, single output feedback control systems is in terms of thinking about what shape you want the open loop transfer function to have across frequency, right? And to think about the design of the controller in terms of compensation of the open loop plant transfer function shape across frequency to give you the desired open loop transfer function shape across frequency, right? Which is not hard to do because the open loop transfer function lambda is just the product of the plant transfer function and C. I think that's the best way to think about control system design, right? And of course, what shape this has to have across frequency depends on what we're trying to achieve. But in general, we're trying to make sure that at low frequencies this has high gain, because that's consistent with getting, small tracking error for low frequency reference signals. It's what's required to get low sensitivity of the output signal for low frequency output disturbances and input disturbances. All right. That's all really about steady state behaviour. Of course, there are transients that the closed loop will exhibit as it moves between steady states, and really that has to do with where the open loop transfer function has gain 1. So it's about what happens at around crossover, right? And we've seen that the phase margin tells you a lot about the nature of the transient response, right? But it's all about the mid-frequency range where lambda makes a transition from high gain to low gain, right? And that's really about the transient behaviour of the closed loop. And of course, to get robustness to modelling uncertainty and low sensitivity to measurement noise, we want the complementary sensitivity function to roll off at high frequencies, right? And how do we make the complementary sensitivity function, which is just lambda and 1 plus lambda roll off? We make lambda small, because if lambda is small, then t will be small, right? So these sorts of things put, upper and lower bounds on where the transition from low to high gain could be, right? It's easy to make the open loop transfer function have high gain at low frequencies. It's easy to make it have low gain at high frequencies. But it's hard to make it transition in a way that gives you a good phase margin. And the key really is to make sure that the slope at crossover is not too steep, right? Which we've seen before, okay? The last thing we've looked at is really just this, pole placement business. It can be combined with the internal model principle. It seems very appealing because, the basic result here says, well, you can always choose the controller to put the closed loop poles wherever you like, right? That seems like magic. But the closed loop poles are not the whole picture, right? And so you've got to be a bit careful and, combine pole placement with the internal model principle to get desired steady state behaviour. So I guess the key message to take away from this subject, right, is that, all of the analysis tools that we've built up can be used to inform design decisions, right? That's the point of developing the analysis tools. It's not just for fun, right? And we've seen how to use them to help us make choices in the design of a feedback controller to meet specifications, all right? But often, to do that, we have to make approximations or focus our attention on part of the closed-loop behaviour and neglecting others, right? And so it's always important to go back and verify that what comes out matches what you want, right? And design is very rarely just this linear process where you start and go make decisions like this and then stop and you're done, right? Design in engineering is always about making approximations, doing something, validating whether or not those approximations make sense. And if they don't, stepping back and making an adjustment to what you're trying to achieve and going through this iterative process until you end up with what you want. Right? There's no this magic plugging numbers into formulas. And if that's the only thing you take away from this subject, I'll be happy. Right? Because, in my experience, people think that everything's just about plugging numbers into formulas, and it's not. All right? So that brings us to the end of the notes, okay? And so on Thursday, we'll look at problem set 5, okay? You're saying, that's how you say where you want the closed loop poles to be. So we're saying we want a closed loop pole that is equals -10, and we want two fairly well damped closed loop poles, right, that correspond to a natural frequency of 3 and a damping ratio of